All right, so we're gonna finish up electrochemistry this morning, and we're gonna do so by first talking about probably the most common application of electrochemistry, which is the battery. So we're gonna explore a couple of different types of batteries and just how batteries have kind of changed over time. And so we kind of want to start with the beginning. The beginning here is something called a voltaic pile. Now, a voltaic pile basically was just a series of zinc and copper plates just stacked on top of each other with some paper discs in between. The paper discs served as the salt bridge, basically. And so you would just stack them on top of each other, and the more stacks that you made, the higher the voltage would end up going. And I mean, as far as functionality goes, it persisted. And the reason it persisted is it worked, but not terribly efficient and used decent amount of resource. So we knew that we were going to eventually need to do something else, something better. Um, Probably one of the batteries that you are the most familiar with is the lead acid battery. The lead acid battery and its variants are used um, in car batteries. Now, the first variation of the lead acid battery was, more or less a voltaic cell, a copper and copper sulfate, zinc and zinc sulfate separation. But what now exists in most car batteries is a series of 6 cells that are in series with each other. And each cell has a voltage just over 2 volts. So I put them together in series. Those of you that have been in physics know, put a series of batteries or any kind of source in series. The electricity basically is additive. This is how we get a 12-volt car battery. Now, the anode in this story is just lead metal itself. The cathode is lead 4 oxide, and it is swimming around in a solution of sulfuric acid. So we've got lead electrodes and a sulfuric acid solution, hence the name lead acid battery. Now, as the battery is being used up, we get lead sulfate in the medium as discharge. But the thing about the lead acid battery that we could not do with the voltaic pile is that the lead acid battery can be recharged. So in your car, you have an alternator. The alternator basically reverses charge and allows the battery to recharge itself while you're driving it. And so you have a system that is effectively, or at least trying to recharge itself as it proceeds. And so the battery goes back and forth, back and forth. And so if we break this kind of apart here, we can see this is more or less a mock-up of what most car batteries look like. And you can see you've got your plates here. You've got your acid solution that's kind of swimming around in it. These bands inside are connecting all the plates together so that they run in series. And then you have your positive and negative terminals here. Which is good for if you wanted to hook the battery up to anything else. Like say you wanted to jump start your battery because it had it fully discharged and you needed to get home. So the lead acid battery is probably the most commonly used battery just in general, given the number of cars that there are. For home usage, dry cell batteries are the most commonly used. And the advantage of dry cell batteries is the metals themselves are less dense. And because they're less dense, they're easier to transport around. I don't need a 4,000-pound car to move the battery from one place to the other, like I would for, say my car battery. Pick up a car battery, it's not exactly the easiest thing to just carry around. It's not a bucket of water. So dry cell batteries usually are composed of zinc and something else. Zinc is plentiful, it's cheap, and it makes a really great anode. As we saw with the reduction potentials, it's reduction potential is like negative 0.76, which means that as an oxidation, you get about 3/4 of a volt when it's oxidized, when it's at the anode. The cathode for a lot of these is manganese 4 oxide, and the cathode and the anode are usually separated by some kind of electrolyte paste, and that's why they're called dry cell batteries. So there's no wet medium in between them. It's some kind of paste usually, and this is why the term battery acid doesn't usually apply when we think about you. If you find if you find a Duracell and you see that stuff's come out of the sides and you go, oh, you got to throw that one away. A lot of people say, oh, be careful, you don't touch the battery acid. It's not actually acid. The paste, the transporting medium, is usually some base solution. So in dry cell batteries, we do have most of them, the alkaline batteries, the primary cell batteries. They can be discharged, but you really can't recharge them, at least not safely. Nickel cadmium batteries are rechargeable, but they do have a shelf life. You can only recharge a battery so many times. This is why the battery in your car eventually does run out and does eventually get replaced. The biggest problem is the nickel and the cadmium are toxic. And so disposal of those kinds of batteries is something that needs to be handled carefully. This is where solid waste management in your town would be called upon to tell you how to best go about that. There are also usually places within any given city that will take used batteries for proper disposal. So these are some mock-ups of alkaline batteries. So this looks like it's maybe a mock-up of a C cell battery, but AA, AAA batteries, D cell batteries, they don't look essentially the same. The negative terminal, the anode here, would be some sort of sealed cap with a pin in it. The pin is just a collector to help distribute charge. And then inside of it, you've got a zinc powder with potassium hydroxide surrounded by a manganese dioxide powder mixed with coal dust. And so the interaction of those two is what generates the charge. And then you've got the positive and the negative terminal for distributing the electricity. A 9-volt battery Works in very similar way, only you have 6 of these cells that are wrapped in series in that ninefold. Um, Nickel metal hydride batteries have been developed over time. They're meant to replace nickel cadmium batteries. They've done a decent job of doing so. How they work is they have basically a nickel anode. So we've got nickel in the +3 state with the nickel oxo hydroxide compound there. And then at the cathode, we have some sort of alloy. And that alloy is composed of one of these 4 rare earth metals, lanthanum, cerium, neodymium, or promethium, for every 5 nickel, cobalt, manganese, or aluminum ions. And so basically, we'll talk about this when we talk about solids at the end of the week, but an alloy is basically just taking advantage of the way that these metals pack and substitute other metals in those positions. And what that does in this case is it allows for some space for hydrogen to come in and settle into the crystal structure. And what the hydrogen does is that's what ultimately provides the ability for the electricity to run. So you take this cathode and anode, you press them onto the opposite sides of this plastic sheet, which is the salt bridge. The whole thing, it has some sort of open vent to the atmosphere to allow hydrogen and oxygen gas to escape. And so what you see is basically a series of layers here. This is known as the jelly roll construction, where you have just a series of layers of these cathodes and anodes separated by the plastic sheet, all wrapped around this core. And the core basically is serving the same purpose as the pin in conventional batteries. It's a place for the medium to go. The difference here, again, we've got the vent valve here that's open to the atmosphere to allow the input and output of hydrogen and oxygen and whatever other gases are necessary. But if you start hearing into conversations about why access to rare earth metals is becoming a more and more um, complex topic of conversation in terms of politics and trade, this is one of the reasons why. Um, we're talking mainly about power, and we're also usually talking about electronics. Not just batteries, but a lot of rare earth metals are finding their ways into computers, computer chips. And since it's pretty hard to find anything now that isn't wired for the internet, including most modern cars, every single hybrid or electric vehicle, if our nation and the world is going to get onto this consumer trade idea of being more electrically powered, um, rare earth metals are a part of that, because right now that's how these things are made. Actually, the article that I'm going to give you tomorrow is about electric vehicles, and some of the challenges that the EV industry is running into. And one of the things that they're encountering is obviously charge time. If you've ever driven an electric vehicle, biggest problem with most electric vehicles that are not some form of hybrid is range and how long it takes to charge the battery. And so there's some really interesting things in that article that we're going to read on that's Thursday morning after this electrochem quiz. Probably the most common electronic battery is lithium ion battery. This is the battery that is used to power things like cell phones, laptop computers. Main reason for its high popularity is they can run at high voltage. We've seen what the reduction potential for lithium looks like. It's almost 3 volts. And that's just for the lithium. Forget what the cathode is. And lithium being such a light metal, 6.9 grams per mole, we can pack a lot of lithium into a small space and it doesn't weigh much. And so what you have is you have lithium layers trapped between carbon layers. Carbon graphite is acting as the anode here. So we've got some form of lithium carbide at the anode and a lithium cobalt oxide composite for the cathode. Salt bridge in this case is a plastic membrane that is porous, so it allows the flow of lithium ions from the cathode to the anode. And so again, we're looking at, okay, what happens? The electrons flow through a wire, and we see in terms of the construction, it's another jelly roll kind of format. But again, the idea here is very, very simple. Lithium ions are transferring from the anode to the cathode, so it's basically acting like its own salt bridge. So as the electrons go from the anode to the cathode, lithium ions are also traveling from the anode to the cathode to prevent it from becoming polarized. And then we can recharge this by basically reversing the process. So we hook this up to an electrical source. We force the electrons to go the opposite direction. The lithium ions also go the opposite direction. It recharges. And that brings us to our final topic for this chapter, which is electrolysis. Now, before we get into the kind of the nuts and bolts of electrolysis, we want to make sure that we get some of our terms and definitions straight. Because when it comes to electricity, there are some things that are used interchangeably that are not necessarily interchangeable. So we've already talked about voltage. Voltage being the electromotive force in terms of joules per coulomb. Or, yes, joules per coulomb. When we talk about current is measured by the ampere, the A, or amps, and by definition, an ampere is 1 coulomb per second. We've already talked about the idea of electrical work when we talked about delta G and E yesterday. Work is measured in joules. Joules is measured as coulombs times volts. We talked about that yesterday. That's where negative NFE comes from. N and F tell us the number of coulombs. E tells us the number of volts. That's how we get delta G and our joules. Power is a measurement of energy capacity. And we measure that in watts. Watts are measured as joules per second. So again, we want to hit this particular point before we got too deep into anything else with electrolysis here, because it's very easy to interchange ideas like current and voltage and talk about them as if they're the same thing. They're not. So we want to make sure that we understand what the distinctions are and kind of where our lines of differentiation are. So with electrolysis, we are talking about something called an electrolytic cell. Electrolytic cells all right, done so well. In electrolytic cells, we have to force the electrical system to do the reaction that we want it to do. So an external source of energy is required in an electrolytic cell. The reactants get turned into higher energy products. What this means is that if this reaction were to run on its own, the E cell would be negative, non-spontaneous on its own. And the amount of voltage that we would have to apply would have to be greater than the E cell in order to get the electrons to flow in the opposite direction. Now, this is precisely what we do when we recharge batteries. When you plug your phone charger into the wall to recharge your battery, what is happening is the electrical current, the voltage coming out of the wall, is basically reversing the discharge process that happened in the ion battery in your phone. And we're forcing the electrons to go the other direction. In the process of going the other direction, we are resetting the battery back to where it was before we started discharging it. Once we take it out of the wall, the battery goes back to being spontaneous. Then it becomes a voltaic cell again. Voltaic cells are when we have the spontaneous reaction happening on its own, doing electrical energy, providing electrical work, doing things like powering your phone and your laptop. It does that completely on its own without your input or interference. That's why it's spontaneous. That's why the E cell is positive. So in electrolysis, we are reversing spontaneity. And to reverse spontaneity, we have to input energy. So the picture here does it a lot better justice. So on the left, we have a voltaic cell. We see that the electrons are naturally flowing from the anode to the cathode. And in the process of flowing from the anode to the cathode, the work can be utilized to generate some kind of load. In this case, it's lighting a light bulb. In an electrolytic cell, we are seeing the process being reversed. So here we have the exact same cell. The electrons are flowing in the opposite direction. But I want you to notice two things. Notice first that our cathode and anode are still describing oxidation and reduction in the exact same way. Oxidation occurs at the anode, reduction occurs at the cathode. That part is always consistent. The part that changed, right here. In an electrolytic cell, the terminals switch sides. So we talked about ANO and CPR in electrolytic cells. ANO, anode, negative pole oxidation, CPR, cathode, positive pole reduction. The only thing that changes is that the poles change. The anode now has the positive pole. So just came up with that one. In electrolytic cell, it's PAN, positive anode, and that's not right. Yeah, that's more like OPE. Never mind. This is why you don't come up with things on the fly. But the thing to remember, the only thing that changes is the positive and negatives switch sides. Probably the most common, other than battery recharging for electrolysis, is electroplating. Electroplating is a process where we can put a very fine film of a metal onto something by basically running it through a solution and electrically charging that surface. If you've heard of gold plating or silver plating, that's basically the process that was being done in those cases. Puts a small surface of whatever metal it is on top of the metal that it's made out of to give it that gold or silver look. So for things like award shows, they're showing here. I think that's process for maybe that's the Oscars. But the gold trophy there, it's not solid gold; it's gold plated. And the process that is being discussed there is actually similar to the process that you read about yesterday. The cyanide gold complex is in solution. You run it through, you put the metal into that solution with a little bit of electricity, and the gold starts to plate itself and ditch the cyanide molecules behind. Now, there are some calculations that we can do around electroplating, but what we need to understand and what we need to know about those processes, we need to know a couple of things. First of all, we need to know what the half reaction is. So more importantly, how many electrons are being exchanged here. We need to know the measurement of current. So how many amps is our current that we're interested in? And we need to know how long the electrical source is running. And so what we can do is we can follow, there's a series of steps that we can start to look at where we go, okay, I can look at current and time. I can look at charge. I can figure out number of moles of electrons. I can kind of go back and forth here. And so what these calculations are going to look like is basically dimensional analysis, stoichiometry, unit conversion stuff. Let's take a look at an example. Calculate the mass of aluminum produced in 1 hour by the electrolysis of molten aluminum chloride if the electrical current is 10 amps. So what we have to remember here, amps. Amps are coulombs per second. So if I look at this, my first logical step is I can see that I have a time here and a unit of current that has time in the denominator. I can probably figure out what to do with that. So starting with my 1 hour time, my first thought would be, well, amps are in units of seconds. I need to convert the hours into seconds. Now, if you don't know that there are 3,600 minute or 3,600 seconds in an hour, you can break this down piece by piece. I know that 1 hour contains 60 minutes. I know that each minute contains 60 seconds. Okay, my hours have canceled, my minutes have canceled. I've got seconds. I know that with this definition of amps, that every second I'm going to get 10.0 coulombs. So my seconds cancel out as well. Now, this is the part that's not necessarily intuitive. So let's go back to the map here and see where we are. Okay, so we had this, and we just figured out the quantity of charge. It says that the next move would be to determine the number of moles of electrons. Do I know a relationship between coulombs and moles of electrons? And it may not come to you immediately, but you should, because we used this value a lot yesterday. Faraday's constant tells us that there's 96,500 coulombs in every mole of electrons. And now here's where we need the balanced equation. So molten aluminum 3 chloride is going to have aluminum 3 ions that we're going to turn into aluminum through this electrolysis process. I'm going to need 3 electrons to do that. Why is this important? Well, looking at this stoichiometrically, 3 moles of electrons will give me 1 mole of aluminum. And now that we're here, well, question asks us for the mass of aluminum. How do I get mass out of moles? Been asking this question since chapter 2 in Chem 105. This is what the periodic table is for. This is the easiest part. Molar mass of aluminum is 26.98. So if I do that long calculation here, and that's all it is, it's just a long stoichiometry, long dimensional analysis. 1 times 60 times 60 times 10 times 26.98 divided by 96,500 divided by 3 to, looks like 3 significant figures, 3.36 grams of aluminum. So after an hour of electrolysis, we get about 3.36 grams of aluminum, not a ton. But this is the kind of calculation that you should be expected to do. Now, there's different exits and entrances to this kind of calculation, but they all kind of wind up in the same way. Doing dimensional analysis in one form or fashion or another to solve the problem. And so while the method is different, the process and the actual calculation work is very familiar. All right, questions so far? All right, let's turn to our final top hat question of the unit here. We have a chromium-3 solution that is being electrolyzed with a current of 7.6 amps. How much chromium should we expect after 2 days? And then second, calculate the amount of amps required to plate out a quarter mole of chromium in 8 hours. So go ahead and try this one out yourselves, and we'll come back and finish it up from here after that. All right, walking around, I can see most of you got through this part already. So go ahead and keep working on the second one for another couple minutes, and then I'll talk to you about how to do it if we're still stuck after that couple minutes. All right, so for a question like this, for number 2, so like I said, everybody seemed to follow the pattern with number 1. It was pretty much the same, only we just had to extend it one step further out in the time dimension because we had to turn days into hours first. But when we're asked to do something like this, where we're asked to calculate current, the trick to that one is understanding, okay, well, what does that mean? Well, what it means is I need coulombs per second. That's what amps are. And so what I should be able to realize relatively quickly is that I'm not going to be able to get coulombs and amps in the same, or excuse me, coulombs and seconds in the same calculation series, because I've got two different things I need to do. I need to turn the moles of chromium into coulombs, and I need to turn the hours into seconds. Now, the first part's pretty easy to do. 8.00 hours. We know that every hour contains 3,600 seconds. So 8 times 3,600 is 28,800 seconds. Now for the amp, or for the coulombs rather, I've got a quarter mole of chromium. And so basically what I need to do is I need to get to the part where I'm basically right here. So I'm going to reverse this process that we did in the previous problem. A mole of chromium weighs 52 grams. Don't need that one. My bad. So 1 mole of chromium is going to give me 3 moles of electrons. And 1 mole of electrons is 96,500 coulombs. So the number of coulombs that are necessary, 0.25 times 3 times 96,500. Now, I'm not going to round this number because I don't want to introduce rounding errors twice. So I'm going to leave this one intact, 72,375. To figure out amps, I need coulombs per second. So 72,375 coulombs divided by 28,800 seconds. I know that this one was to 3 sig figs and this one's to 3 sig figs, so my amps are going to be to 3 sig figs. So 3 sig figs, 2.51 amps. Would be the correct answer there. And that's basically the extent of electrolysis kinds of questions. So, like I said yesterday, these calculations are not terribly difficult. So if you went to try them yesterday and were able to figure them out, that's great. That makes things a lot easier for you. If not, it won't take very much for you to go back to look at it tonight. And they generally follow one of two patterns here. We are either trying to figure out voltage, or we're either trying to figure out current, or we're trying to figure out mass, or we're trying to figure out duration. And so if we're trying to figure out duration, basically we just reverse the purple process. We're starting with how much did we make, and we're reversing it until we get to how long did it take. If we're doing amps, then we split it up like I just did and kind of tackle each part in turn, use the definition of amps to figure out what we need to do. And then we've already done 2 examples of how to convert it into mass. The only other variant on that would be to determine the number of moles, which just is the same process. We just stop one brick shorter. Any questions with electrolysis? All right, that is it for this unit then. So let's go ahead and take a break.